To solve the same problem the other way, using the motional EMF, we need to look at how each of the sides of the loop is moving in relation to this magnetic field. Now, if it's rotating clockwise from our point of view like this, remember our coordinate system is up is the Z direction, X is to the right, and Y is into the page. Look what happens to each of these sides. I'm going to give them numbers. If this is side 1 is always along Y. And side 2 seems to, if we were to break it up into little differential length elements, DL is going to be some amplitude. DL is going to be partially along X and partially along Z, depending on where you are in the rotation. So if you remember, this is the surface normal vector, n hat, which is also a function of time, and we wrote that as x hat sine omega t plus z hat cosine omega t. So what would that differential length element be? Well, it's an element that is perpendicular to both n and y. So if we did y cross n hat, we would get what that element is. Let's see, do we need to do y cross n hat, or do we need to do, yeah, we need to do y cross n. So y cross that stuff, if we write that out this way, x hat, y hat, z hat, we're using the determinant method, 0, 1, 0, sine omega t, 0, cosine omega t. And if we do this determinant, we're going to get x hat cosine omega t from this little square. And over here, we're going to get minus z hat sine omega t from that little square. So that is the unit vector along DL for that side. Actually, by the right-hand rule, it needs to point that way. So my contour direction needs to be like this in order to agree with the surface normal vector that I chose. That means that DL is x hat cosine omega t dx minus z hat sine omega t dz. It's always got the same magnitude, the magnitude of any differential length unit, but its direction is going to change. And that's for number 2, which is pointing to the left, which actually means that there needs to be a minus sign on the front of this whole thing. And number 3, that would be over here. That's also along y. Here, on number 1, dl is pointing in the minus y direction, so it's minus y hat dy. On side 3, dl is in the plus y direction, so it is y hat dy. Now I need to erase some stuff so that I can talk about side 4. And then side 4 over here has the same sort of situation as side 2 did, but this dl is to the right instead of to the left in the picture that we're currently looking at. So dl for that one is going to be plus x hat cosine omega t dx minus z hat sine omega t dz. All right, so how do we figure out what the induced EMF actually is? When you are using the motional EMF method, remember that VEMF is this contour integral of the effective electric field, where that electric field represents U cross B. So now that we've figured out what dl is, we also have to figure out what the value of u, the velocity of each little segment of the loop is. Sides 1 and 3, that's an easy thing. I'm going to draw it in red so you can see. It is parallel or anti-parallel to the surface normal vector, and it has magnitude u is equal to, on side 1, omega a over 2, where a is the side length of that square, times n hat of t. And that's on side 1. And on side 3, it is the same but negative, so it's minus omega a over 2 n hat of t on side 3. On sides 2 and 4, the velocity is going to be x-dependent because it depends on how far you are from the axis. If we choose a point that's at the corner, that point is moving faster than a point that's really close to the axis that it's spinning around. On sides 2 and 4, it is omega x over 2 minus sign n hat of t. And those are all of our velocities. Looking at these different velocity expressions along each of the different sides, you see that all of them contain the surface normal vector n hat right there. And remember that B is a uniform magnetic field that is z-directed. So that's just equal to that. So in order to simplify the work that we have to do later, we're just going to compute n cross B right now, because then we'll have the building blocks of U cross B. So remember that n hat was x hat sine omega t plus z hat cosine omega t. So if we do that and we cross n hat with z hat b naught, writing down my determinant method cross product just like I usually do, I have got sine omega t right here. I've got cosine omega t right there. 0, 0, 0, 1, like that. And then I take my little determinants. I'm going to get no x component. I'm going to get a y component that is sine omega t, negative sine omega t, minus y hat sine omega t, and I'm going to get no z component. So that is the cross product there of those two unit vectors. So n hat cross z b naught, if I put in the amplitude of b naught there, then I'm just going to get a b naught on the end. Let's take this back and look at what we're going to do with it. Remember that what we're doing is the contour integral of E dot dl. And we've just found using this cross product that that effective electric field is y-directed. So it's only going to contribute on sides where dl is also y-directed. Otherwise, we're going to get 0. And dl has to have a y component. Going back up and looking at the dl's that we calculated, we only have a y component on sides 1 and 3. Sides 2 and 4 don't have a y component on dl. There's 1 and there's 3. Well, that makes it easy because that also is where the velocity is constant. That's 1 and that's 3. X is that way, and y is that way, and z is up. So the thing is that as much as this loop rotates, sides 1 and 3 stay y-directed, even though the directions of sides 2 and 4 change. So VEMF is going to be the contribution from side 1, which is going to be the integral from y equals minus a, no, that's positive a over 2. Y equals a over 2 to minus a over 2 of, what's my expression for the velocity? Okay, omega a over 2 n hat. Oh yeah, we already did this cross product. So instead of an n hat there, we get to put in that n hat cross z hat b naught, which just becomes minus y hat sine omega t b naught. And then we dot that with dl, which in this case is minus y hat dy. Plus, and this is the contribution from side 1, and now we have to do the contribution from side 3, which is going to be the integral from y equals minus a over 2 to a over 2, omega a over 2, minus n hat cross b, so that's going to be y hat sine omega t b naught, dotted with dl, which in this case is going in the plus y direction, so that's y hat dy. So then, by evaluating this, minus y dot minus y gives us 1. All of the other terms are constant, so we're just integrating along y. And we can flip the bounds, and that's fine. And then we get a. We get a factor of a. So VEMF becomes omega a squared over 2 b naught sine omega t. That's the contribution from side 1. Plus, well, this one works out the same way. We do this dot product. We integrate from minus a over 2 to a over 2 along y, a bunch of constants, plus omega a squared over 2 b naught sine omega t. So VEMF becomes omega a squared b naught sine omega t, where that a squared is the area of the loop. And if we look back, when he calculated this based on VEMF is the negative time derivative of the flux, we got the same answer, omega a b naught sine omega t. So doing this the motional way or the more transformer-like way got us the same answer both times, which is how it should be.